Hi everyone, my name is Ganesh Pakar and I am a postdoctoral research associate at University of California, Santa Barbara. The title of my talk today is Spin Excitations in Multifaric Scormion Host GaV4S8. This work was done at University of Tennessee in Oak Ridge National Laboratory when I was a graduate student at University of Tennessee. I want to thank to all my collaborator who has a great contributions to continue this project before I go into detail about my presentations. Most of my collaborators, they are affiliated to University of Tennessee, Oak Ridge National Laboratory and Niche Center for Neutron Research. Meantime, I want to thank to my funding provider, Gordon and Betty Moore Foundation and Department of Energy Office of Science for their support to continue this project. These are the outline of my presentation. First, I will briefly talk about the Lacunary spinel structure and the formation of new molecular cluster in these materials. Then I will enter into the material which I'm going to present today, that is GaV4 acid, and then motivation behind it. I will talk about the synthesis procedure of this material and then the measurement detail and the visualization of data coming from the inelastic Newton scattering measurement, and then finally I'll conclude with few concluding remark. Basically, the lacunar spinel structure is formed by the normal spinels with chemical formula Am2X4. The absence of alternate A-side metal ion in normal spinels that rearrange the M4 tetrahedral cluster, resulting a periodic expansion and contraction of tetrahedra, forming a lacunar structure. In lacunar spinels, the bond length between the magnetic ions in small tetrahedra, that is small, due to which the magnetic ions, the d orbitals, they overlap with each other, forming a molecular cluster. In case of GaV4 acid, there is a single spin which occupy a triplet degenerate T2 molecular orbitals. As a result, this material is highly orbitally active, resulting orbital ordering at low temperature below 42 Kelvin. For the orbital ordering, the material elongate along the high symmetry 111 directions. As a result, the triplet degenerate T2 orbital splits into doublet degenerate En and non-degenerate A1 orbitals. GaV4 acid is attracting a lot of attention these days because of the rich phase diagram. Although the material has non-chiral polar crystals, it exhibits a Scormion structure, which was theoretically predicted long time ago, although it took some time to observe experimentally the Scormion lattice in non-chiral structure. You can see in the slide that these material host multiple magnetic ground state, including nil type scormion, cycloidal ground state, and conventional ferromagnetic ground state. Although there are certain literature available in the market which talk about the static structure on these materials, but there is a very limited work which explain about the dynamic structure. The absence of such studies is due to the inability of having larger single crystal of this material which scatter in inadequate amount of newtons, giving showing some dynamic structure in the system. So my motivation is to look into the dynamic structure to understand the spin interactions between the neighboring magnetic vanadium ion. Uh, Now we have the motivation of our project. So for this we need the sample. So the sample is grown using a conventional solid state reaction technique, which was followed by chemical vapor transport for the single crystals. And I grew the single crystals of around 100 milligram in size, which is one of the biggest single crystals that is available in this material. And this inelastic Newton scattering measurements on single crystals, they are carried out at max NCNR or NIST. Before showing you the inelastic data, let me show you the powder average spin excitation spectrum, which I measure at CNCS SNS Oak Ridge National Laboratory. From the powder average data, we can see that the spin excitation spectrum has zone boundary energy around 6 MeV. The zone center looks close to Q is equal to 0, but the resolution limitation of the instrument, we cannot able to look into the dynamics at Q is equal to 0. Once we have some ideas about the spin excitation spectrum from powder average data, I co-aligned some certain number of single crystals with total mass around 1.2 gram along the scattering plane HHL, and the co-alignment is pretty good with the crystal mosaic less than 1.5 degree. And the last figure in this slide, which shows that the temperature dependence intensity, indicating that there is some magnetic scattering at below the magnetic ordering temperature, 13 Kelvin on this temperature, showing some higher intensity at 1.7 K compared to 20K or 50K data. These are the spin waves which I measure from the co-aligned single crystals. The first two figures represent the spin wave along the high symmetry direction O1 and 110 directions. The spin wave along 110 direction, it shows some slopy feature or asymmetry around the zone boundary. And the third figure is the line curves at different region in the reciprocal space, and the last figure in the slide that indicates the constant energy cut, and the circular region shows the constant energy portion of the spin wave cone in this material. For this plot, we took the constant energy 3 MeV. Once we have the data, now we need to visualize the data. For visualization, we need model. For model, I use the simple Heisenberg spin Hamiltonian with the DM interaction and G-man term. First, I didn't consider the DM interactions, but without adding DM interactions, I couldn't able to reproduce the slopy feature of spin wave along 110 direction. So DM interactions is mandatory at the temperature of 2 Kelvin 2. And for the model, we know in this material that there is a single spin that is associated with the B4 tetrahedra. So I localize the spin at the center of mass of each tetrahedra, and then model the spin excitation. By doing this, I could able to reproduce the excitation spectrum which we measured experimentally. The upper panels represent shows the theoretically calculated excitation spectrum, and the lower panel, which I showed in the previous slide, that is the experimentally observed spin waves. The spin waves obtained from the model is has the same energy scale, and the feature are very close, meaning that the model is capable of reproducing the spin excitation spectrum. Based on these simulations, we observed the nearest neighbor exchange coupling around 0.7 MeV, which is strong ferromagnetic, and the DM interaction is around 0.1 MeV, meaning that the DM interaction is around 15% of nearest neighbor exchange interactions in this material. Now I'm showing the line course and the fit of line course along the high symmetry direction O1 and 110. The fitting of the constant energy from 2 MeV to 6 MeV along these two high symmetry directions also indicates that the model is completely capturing the feature in this material. What about the powder average data? Does the model replicate the powder average data? Yes. The left hand side and the right hand side represents the experimentally observed and theoretically calculated spin wave spectrum. The zone boundary energy and all the features of excitation spectrum is very close to each other, meaning that the model is reproducing the powder average data too. To check either the model works at field or not, we carried out some inelastic measurements at field, but due to the large background from the sample magnetic field sample environment, it is hard to compare the zero field and magnetic field data. Although at field of 1 Tesla, we observed that the energy scale is slightly higher compared to the zero field data. These are the outline of my talk. Even the temperature of 2 Kelvin, we observed some finite DM interactions into the system. Thank you for your time. Now I'm open for the questions.